well. So let's continue the topic of series. Today we're going to talk about power series, and then we're going to try to approximate some functions using power series. Well, the very first definition. Definition of power series. So a power series in general defined this way. A power series is defined as the sum C sub n x minus a to the power n starts from 0, goes to infinity. So what are you doing? You're adding a variable to our series, actually a new variable, which in this case is x. So we can write the terms of this series this way. If n is equal to 0, what I have c sub 0 x minus a to power 0 plus. If n is equal to 1, I get c sub 1 x minus a to the first power plus. If n is equal to 2, I get c sub 2 x minus a to the second power plus the rest of the terms. In a special case, if a, it's just a number, is equal to 0, or a equal to 0, we can write this power series in a shorter form. We get the sum Cn x minus 0 to power n, or just x to the n, and starts from 0 to infinity. So the terms of this power series when a is equal to 0 is c sub 0 x to power 0 plus c sub 1 x to the first power, c sub 2 x to the second power plus the rest of the terms. So x to the power 0 is just 1. We can write it as c sub 0, c sub 1x, c sub 2x squared plus the rest of the terms. And in this case, we have c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus the rest of the terms. As you can see, these are very similar to polynomials that you learn in intermediate algebra. Recall that a polynomial was like this. Polynomial of degree or power n degree n is defined as p of x equals to a sub 0 plus a sub 1x plus a sub 2x squared plus the rest of the terms. So as you can see, a power series when a is equal to 0 is very similar to a polynomial. Very well. In the next step, we're interested in analyzing power series. As a calculus student, you should be asking, hey, now that you're defining a new series, when it is convergent, when it is divergent. So question, when a power series convergent or divergent. There we go. So we defined a power series in general form Cn x minus a to the power n, and when A is equal to 0, we have this case. We have the sum Cn x to the n, and starts from 0, goes to infinity. When it comes to convergence and divergence of these series, we have 3 different cases. First case is very easy. We assume that x is actually equal to a. If x is equal to a, what's the meaning of that? It means that this term is going to be 0. 0 to any power is going to be 0, and here you have c sub n. So you're going to get the sum of Cn times 0, which is equal to just 0. It means that you have a convergent series, it converges to 0. It's a very trivial case. We're not interested in trivial cases. Second case. We are interested in looking at this series and saying that, hey, for which values of x we have a convergent series. We have a convergent series. And finally, how can we find a number like r that we call it the radius of convergence, that we can bound the distance between x and a somehow using r and decide about convergence and divergence of power series? This is our third case. What is r? Value r is called the radius of convergence. Such that when we find the distance between x and a, and we can bound the distance by r, we get a convergent series. Become convergent. And when x goes far away from a, the distance is getting larger and larger. It means that it gets larger and larger. Our series is divergent. It becomes divergent. So we're interested in these scenarios. Let's take a look at one example. Okay, here's defining a new power series. Example. Let our power series be defined this way. The sum -3 to the power n times x to the n divided by square root of n plus 1, and starts from 0, goes to infinity. Let this series be a power series. Find the radius of convergence and the interval of convergence. Find the radius and interval of convergence. Okay. We're finding that distance between x and a such that this power series is convergent on that interval. Very well. So we're solving this example, let us review what we learned before about the ratio test. So recall that. The ratio test tells us if the limit of absolute value of an plus 1 divided by an while n goes to infinity is equal to L, and that L is less than 1, then for sure we have an absolutely convergent series. Then our series is absolutely convergent. Okay, here we go. To analyze your power series, you're going to use the ratio test. So, to analyze the convergence of a power series, we use the ratio test. Okay, ratio test tells us the limit of absolute value. Let me write it down here, I need more space. The limit of absolute value of an plus 1. It means that whenever we see n, we have to substitute that by n plus 1. So we get negative 3 to n plus 1 times x to n plus 1 divided by square root of n plus 1 plus 1. The whole thing is divided by negative 3 to the power n, x to the n divided by square root of n plus 1. We take this limit while n goes to infinity, it must be less than 1. Okay, perfect. Well, this is limit. This limit can be written as, so we're going to multiply the first numerator and the last denominator, negative 3 to the power n times negative 3 times x to the n times x times square root of n plus 1 divided by, and we're going to multiply the first denominator and the second numerator, and we get negative 3 to the power n, x to the n, square root of n plus 2. Then we send n to infinity. There you go. As you can see, you can cancel out the common factors, negative 3 to the power n, negative 3 to the power n. And at the same time, you have x to the n and x to the n. Recall that the limit of square root of n plus 1 divided by square root of n plus 2 while n goes to infinity is equal to 1. So it tells us that this limit by the ratio test must be less than 1. It means that we get the absolute value of negative 3 times x is less than 1, or 3 times absolute value of x less than 1, or absolute value of x is less than a third. This is your R. Radius of convergence is a third. R is a third. Radius of convergence. We're not done yet. Now we need to check the lower bound and upper bound and substitute that for x in the original series to check to see if you have a convergent or divergent series. Okay, so I'm going to plug the lower bound and upper bound into the original power series to analyze the series. So let me write this right here for you. So here, 3 times absolute value of x less than 1. So absolute value of x is less than a third. It means that your x is bounded between negative a third and positive a third. So the lower bound is negative a third and the upper bound is positive a third. Lower bound. And this is your upper bound. So when x is equal to negative a third, what happens to our original power series? When x is negative a third, we get the sum of negative 3 to the power n, negative a third to the power n. So instead of x, you substitute y negative a third, divided by square root of n plus 1. So you can cancel out these two. You get the sum 1 divided by square root of n plus 1, and starts from 0 to infinity. This is what you saw before. Is this convergent? Is this divergent? Can we accept negative a third? What if I plug in upper bound? What if my x on the boundary is exactly a third? What happens here? Here we have a series and ranges between 0 to infinity, negative 3 to power n, times now a third to the power n, divided by square root of n plus 1. If we simplify this, we get the sum negative 1 to power n, divided by square root of n plus 1, n starts from 0, goes to infinity. The same here. Is this convergent? Is this divergent? Well, by using limit comparison test, this series is a divergent series. By limit comparison test, it is divergent. What about this guy? This series is a convergent series. This is an alternating series. Alternating, convergent series. Well, so what's the meaning of that? It means that negative a third is not acceptable for us. So not acceptable. But a third is acceptable. It means that our interval of convergence, so the interval of convergence is going to be negative a third to a third included. It means that if you take any x value between negative a third to a third is included, this power series is a convergent power series. If you take any other number outside this range, you get a divergent series. That's the meaning of that. And remember that R is equal to the radius of convergence. So we have radius of convergence and we have interval of convergence. Radius of convergence gives us the information about numbers inside the range, not on the boundaries. For the boundaries, we have to get back to the original power series and check to see if the power series is convergent or divergent. Perfect. So let's go over one theorem. We're going to use power series to actually approximate functions. How do we do that? We have a nice theorem for that. Theorem. Suppose you have a function. Let f be a function. And suppose it has a power series representation or power series expansion of this form. If F has a power series expansion of this form, f of x can be written as the sum Cn x minus a to the power n, and starts from 0, goes to infinity. And note that your power series must be convergent over an interval. Absolute value of x minus a must be less than r. So the distance between x and a is less than a positive number like r. Then these coefficients have relation between the derivatives, different power derivatives of the function. Then the coefficients C sub n are defined this way. So C sub n is defined as the n derivative of function evaluated at a divided by n factorial. Okay, what's the meaning of that? So before writing C sub 0, C sub 1, C sub 2, and the rest of them, remember how we define the different derivatives of the function, the power derivatives. Recall. So f to power 0 in parentheses is the same as your function. F to the first power, or f prime, is the first derivative of the function. The first derivative. F to the second power in parentheses is f double prime, the second derivative of the function. The second derivative. So the third derivative, the fourth derivative, instead of using primes, you're going to write down, hey, this is the third derivative of the function, then the fourth derivative, the fifth derivative, and then f to power n inside parentheses is the nth derivative of the function. Nth derivative. Okay, so when you see f to power n in parentheses, it means that you're taking the derivatives of the function. So c sub 0 is equal to the zeroth derivative of the function at a divided by 0 factorial. Very well. So we know that the zeroth derivative is equal to function f, and we also know that the 0 factorial by convention is defined as 1. So this is equal to f of a. C sub 1 is the first derivative of the function evaluated at a divided by 1 factorial, or f prime of a just divided by 1, or f prime of a. C sub 2 is the second derivative of function evaluated at a divided by 2 factorial. C sub 3, the third derivative of the function evaluated at a divided by 3 factorial, and the rest of them. So to write the expansion for any function using a power series, convergent power series, we need to have the derivatives of the function. So if you need to review the derivatives that you learned in elementary calculus, please get back to your notes to the previous lectures in elementary calculus and review the derivatives of different functions. In a special case, if a is equal to 0, the actually have a name for it. We call it a Taylor series.